In this lesson, we are working on more basic functions, so basic functions day 2, with something that is called a piecewise defined function or a piecewise function. So when a function is defined by different equations on different parts of its domains, it's called a piecewise defined function or a piecewise function. Here, example 1, this is what it kind of looks like. Here's the function f, and the function f is 2x plus 3 when x is less than 0, and then it switches to be negative 1/2 x plus 3 when x is larger than or equal to 0. So we're going to have two different parts of this graph, two different parts of this function defined by the red equation and then the blue equation. Okay, so some things we're going to do with these piecewise functions, we're going to evaluate them, so plug in some numbers, we're going to find the X and Y intercepts, we're going to graph them, and then we're going to work backwards, and from a graph, we're going to write our functions. It's our 4 goals for today. In the first example, we have the red equation and the blue equation that make up f of x. Okay, I like to separate mine by color, but it is truly one function, all right? Now, if I want to find, so part A, I'm going to evaluate some values here. If I want to find what f of negative 2 is, I'm going to be plugging in negative 2. But I have to decide if I'm going to use the red equation or the blue equation to do the function evaluation. The way that I do that is I have to figure out where x is negative 2, which one of the two equations I would use. So in this case, f of negative 2 is where x is less than 0. So I'm going to actually use that red equation, and I'm going to be plugging in negative 2 or evaluating f of negative 2 using that top equation, the red one, since that's where the domain is. So you would get, just multiplying and adding here. So you would know that f of negative 2 is equal to negative 1. Okay, if we did the second one, f of 0, I'm looking to figure out where in the domain on this function f I actually can plug in 0. And that's on this blue section because it says x greater than or equal to 0. So I would plug in 0 to that function. Evaluate 0 f of 0, which would just give me 3. So we have another coordinate point, f of 0 equal to 3. And last but not least, we want to evaluate f of 2, which again would mean that I want to use the part where the domain is larger than or equal to 0. So I'm going to plug in 2 to the blue equation, the second part, because that's where it's defined on its domain. And then I just do some multiplication and addition, and I would get that f of 2 is equal to 2. Okay, now we can use this information to graph these functions. I recommend plotting the coordinate points that you have, like negative 2 comma negative 1. That's the coordinate point we've already evaluated. 0 comma 3, and then 2 comma 2. And then to make sure that you're doing this right, you need to find more coordinate points. I recommend remembering that these equations up here are written in mx plus b. Some of them will be quadratics, but for this one, they're both linear, which means we have a slope, a rise over a run, and a y-intercept. If I start at the red coordinate point I've already graphed and I utilize the slope of that line, which is 2, it means I'm going to go up 2, boom, boom, and over 1, and create more coordinate points so that I can draw a straight or semi-straight line if you're me and can't draw a straight line to save your life. And if we were zooming in on this, because it's not equal to 0, there would be technically a red open space right there. However, because this function also begins at 3 here, you have a closed blue one, so truly it's a closed line, and you could play connect the dots. Now, that is my piecewise function, and because I've drawn it in 2 separate colors, it looks like it's 2 different things, but truly, this f of x function is all of this. That is the entire piecewise function. Okay, we can think about it as 2 parts because it has 2 separate functions on different domains, but the whole thing is one function. Okay, I'm going to have you guys pause the video, and I just want you to try example 2. Truly pause it and try it before you look at the answers, because I'm just going to pop the answers up on the screen. But for example 2, you're just going to evaluate f of negative 5, f of 0, and f of 4. So if we get ourselves started on this, we have f of negative 5, f of 0, and f of 4. If I look at the domains for where x can be negative 5, that would be the red part, the top function. So we're going to be plugging negative 5 into the first part of this piecewise function. Negative 5 squared plus 1, which is 25 plus 1, or 26. So we know that f of negative 5 is equal to 26. F of 0, you'd want to plug it into the second part of the equation because that's where it's defined on its domain. So we know that f of 0 is equal to negative 1. And last but not least, f of 4 is also within the blue domain, the second part's domain, because x is greater than or equal to 0 there. So we know that f of 4 is equal to 3. Woohoo! Moving right along. Now, this kind of utilizes what we know about X and Y intercepts as well as evaluating functions and looking at domains to be able to do this. So one thing I want you to remember is that if you're looking for X-intercepts, that means that the y is 0. Every X-intercept is partnered with a y of 0 because it's going to be a number comma 0, which means we know that we can set y equal to 0 and then solve for x to find the x-intercepts. And with y-intercepts, we know that these are always 0 comma some number, which means we can plug in x equal to 0 and find the y-intercepts. Now, determining the x-intercepts is a little bit more complicated than the y-intercepts, but it's pretty cool. So here's what we're going to do. We have 3 parts to this equation. We have the black part, the red part, and the blue part. Okay, I'm just going to call them different parts. And what we're going to do is we're going to set each of these parts, the black, the red, and the blue, equal to 0. Okay, because f of x is the same thing as y. So if I'm trying to find the x-intercept, I need to set all of the parts of this function equal to 0. We're going to solve all of these 3 parts of this function for x. So minus 4 on both sides, you'd have minus 4 equal to x. Okay, x equal to negative 4. But after I do that, I can't just assume that that's my y-intercept. We have to make sure that for the black part's domain, which remember this domain is only if x is between negative 2 and 1, is negative 4 within this domain? No. So we actually can't even use that as an x-intercept because this function doesn't exist where x is equal to negative 4. Hopefully you're looking at the red part of this equation and you're like, Miss Quigley, 0 does not equal 8. You're right, that's automatic, it's out, gone. But if we add x on both sides to the blue equation, we get x equal to 3. The domain for the blue part is where x is larger than 1. Is 3 larger than 1? Absolutely, that one checks out. So we know we have an x-intercept at the coordinate point 3, 0. Now, your piecewise function may have more than one x-intercept, so don't just stop when you found one and say I've found my x-intercept, because you might have more than one x-intercept. But it is a lot easier, in my opinion, to find the y-intercept because you don't have to test 3 different parts, 3 different subintervals here. What you would do is you would plug 0 in for x. Which of these 3 intervals, the black, the red, or the blue, has 0 within it? That first one. 0 is between negative 2 and 1. So all I'm going to do is plug in f of 0 to x plus 4. So I just plug in a 0. Like I said, Miss Quigley, come on, get it together. We'd have f of 0 is equal to 4. That means that my y-intercept is the coordinate point 0, 4. And that would be really helpful if I was graphing these to know the different intercepts, since they're pretty easy points to plot on a graph. Okay, again, for example 4, I want you to go ahead and pause the video and find the x and y intercepts for this new f of x function. So here's what we would have done for this problem. You would have set each of the intervals the subintervals equal to 0. Then we're going to solve them to see which one of them exists during its domain. So if we solve this for x, we're going to have -1 equals to -2x, and then x is equal to +1/2. Now, +1/2, is that within this black subinterval between -3 and 1? So -3 is less than or equal to x is less than 1. Is 1/2 within that interval? Absolutely. That's going to be one of my x-intercepts. Let's see if there are any more. Okay. Yeah, 0 doesn't equal 2. No way. Doesn't work out. If we take the square root of both sides, we're going to have the positive and negative square root of 0 equal to x. And square root of 0 is 0, and it doesn't have positive or negative attributes, so 0 is equal to x here. Is 0 equal to x, or is 0 greater than 1? No. So that's not one of my intercepts either. My only x-intercepts for this graph is at 1/2, 0. That's my x-intercept. For my y-intercept, I would just plug in 0, but I have to make sure I plug it in to the interval where it exists, which is, again, this top one between -3 and 1. That's where 0 is. So I'm going to be plugging in 0. This would be 0 plus 1 or 1. So we have a y-intercept at the coordinate point 0, 1. That's my y-intercept. Hopefully that went pretty well for you. We've gotten through a lot of skills. We've evaluated these piecewise functions. We've used them to find intercepts. So let's start graphing them. I kind of showed you a little piece of this earlier, but we're really going to get into graphing them more accurately now. It's going to be very helpful to have a table of values prepared for this one. So we're going to make our own table of values. I'll make these two different colors again. So we're going to have the red equation and the blue equation. And we need to evaluate some x and y's for both of those intervals. And I'm going to make an x and y graph or a chart here with some space in the middle so I can actually calculate these things. If you look at the red subinterval, it says as x is less than 1. We probably need 2 to 3, maybe 4 coordinate points that are less than 1 on our chart. I always like to do -2, -1, 0, 1, and 2 if possible, which means we'll evaluate -2, -1, 0, and 1, but only from the negative side because it is not equal to 1 in this interval. But I can still evaluate what it's getting closer and closer to. So if I plug this in, -2 squared plus 2, that's going to be 6. -1 squared plus 2 is going to be 3. 0 squared plus 2 is going to be 2. And 1 squared plus 2 is going to be 3. So I have the coordinates of -2, 6, -1, 3, 0, 2, and I would have technically an open circle at 1, 3. So I'm going to draw my open circle because remember it's not equal to right there, but it's headed back up that way as we get closer and closer to it. If we switch to the next one, the next interval is just things between 1 and 3. So you have 1, you have 2, you have 3. Let's evaluate those things. Can't do 4 because 4 is not within the blue domain in that subinterval. So 3 times 1 minus 5, that's -2. 3 times 2 minus 5, that's going to be 1. And 3 times 3 minus 5, that's going to be 4. So I have more coordinates to plot. I have 1, -2. I have 2, 1, and I have 3, 4. Once you have all of your dots plotted, you can play connect the dots. Starting on the left side, we had an arrow because it doesn't have 2 endpoints. We're going to come up to that empty space right there, and then we're going to jump. This is a discontinuous graph. We're going to jump down because we switched from the red equation to the blue equation. I'm using air quotes, but you can't see me. The red equation, air quotes, and the blue equation. Remember, all of these, it is one function. This is one function on our graph called f of x. We just do them in two parts because it is defined by two different functions at different points in its domain. This next graph, I'm going to let you try both of them. So go ahead and try both to graph both of them. For the first one, I'll give you some training wheels here. I'll give you the X and Y coordinates that I suggest to use to evaluate. For this one, I suggest using -2, -1, 0, 1 from the negative side, and then also 1, 2, and something else like the endpoint of 6. Okay, pause this video, give both of these a shot. I'm going to have the answers pop up on the screen, so really try it on your own first. All right, if we start doing this one, again, we look at slopes and y-intercepts. The slope of the red segment of this piecewise function goes up 2 and over 1, so its slope is 2, and it crosses that y-axis at 2. So my equation here would be y equals to 2x plus 2, and this occurs between the x-coordinates of -1 and 0. In interval notation, that would look like this, but we want inequality notation. For the blue segment, it has a slope of 1 and a y-intercept, or would-be y-intercept, of 0 if it existed there. So its equation is y equals 1x. And this graph appears anything that's larger than 0, right? From 0 to infinity. So we just have to put these pieces together. We would say that f of x is equal to 2x plus 2 if x is between -1 and 0, inclusive on both sides. And then f of x is equal to just x when x is larger than 0. That's my red and my blue part of this one piecewise function. So piecewise functions take a lot of what we know, little bits and pieces of things we've been practicing for a while, and puts them together. Since we're just graphing functions and we just switch what part we're using at different domains. So make sure you pay attention to those domains as whether they're inclusive or exclusive, so open circles and closed circles, to make sure that you got all of this down. Bye everyone, see you in class.